Hello everyone, and welcome to this demo of the first ESB Journal Club. My name is Syed Ali Elahi. I'm a postdoctoral researcher in KU Leuven, and here I'm going to talk about the integrated in silico cartilage degeneration framework I developed in the context of my Marie Curie individual fellowship. The work is published in this paper in collaboration with 3 different groups at 3 different departments of KU Leuven and Department of Applied Physics in the University of Eastern Finland. Cartilage is a soft tissue covering the end of the bones within the joints and is vital to absorb the shocks and reduce friction during movements. A perturbation from healthy state of cartilage can be happen due to different drivers, like injurious loading, presence of defects, or biochemical degradations. These are drivers of cartilage degeneration and osteoarthritis, which consequently causes pain within the joints and limits the movements. Experimental observations suggest that during osteoarthritis, the cartilage microstructure is altered. To prevent osteoarthritis and target therapies, these 2 questions have to be answered. Are the different drivers alter the cartilage microstructure in the same way? And what is the interactive effect of degenerative change in different microstructure components? It is challenging or even impossible to answer these questions using a state-of-the-art in vivo or in vitro experiments. However, in silico modeling can open a new window through simulating cartilage microstructure and studying the interactive degenerative change in cartilage constituents due to different osteoarthritis drivers. This was our motivation to introduce our cartilage adaptive reorientation degeneration, or in short, CARED model. For simplicity and comparability with in vitro experiments, we made a finite element model of a cylindrical cartilage plug. The finite element model accounts for cartilage microstructure that is mainly consists of collagen fibrils, negatively charged proteoglycans, and a solid fluid biphasic structure. Furthermore, it accounts for the depth-dependent distribution of the cartilage microstructure contents. To simulate degeneration of microstructure under mechanical loading, an unconfined compression was applied to the cartilage explant. And as a result of the finite element simulation, the local strength sensed by fibrils and solid matrix were determined, based on which the degenerative change in the microstructure of the cartilage were determined. The degenerative changes were degeneration and reorientation of collagen fibrils, loss of negative charge density due to the loss of the proteoglycans, and loss of the solid phase. The new contents were inserted as the input into the finite element simulation for the next iteration, and using this iterative simulation, the CARED model can simulate the main experimentally observed degenerative change within the cartilage microstructure. For the analysis in this study, we simulated 3 different groups of cartilage explants. First, a normal cartilage explant that was an intact explant under normal loading estimated with 2 MPa unconfined compression in 0.1 second. Second, an injurious loading explant that was an intact explant under 4 MPa load in 0.1 second. And third, focal defect models that were the cartilage explants with focal defects as shown in the figure with different depths representative of different ICRS grades under normal loading of 2 MPa unconfined compression in 0.1 second. As a result, the model could predict collagen reorientation, collagen degradation, loss of negative charge density, and loss of solid phase. Here, an example of the result for injurious loading model is shown. And then we could compare these results with microscopy measurements within the literature under injurious loading. We could also compare the degenerative change in cartilage explants with different defect depths and reach interesting conclusions. Are you interested to know more details and discuss our approach? Then I'm looking forward to meeting you at ESB Journal Club on 8th of March.